Hello, everyone. It is my honor to be giving this keynote at the Indigenous Agriculture Innovation Conference. I'm Ranveer Chandra. I'm at Microsoft. I've been with Microsoft for 16 years. And in my current role, I serve as the CTO for agriculture and food. I started the FarmBeats project in 2015. And the goal of the FarmBeats project was to enable data driven agriculture. The reason I started this project was one of the reasons was that I grew up in India. I grew up in Jamshedpur. It was a city, but every summer and winter vacation, I would go to this farm in Bihar, which is a state, a very rich but poor state in India. Back then, I did not like anything to do with agriculture. These farms, they were small farms. The villages did not have any electricity. They did not have any toilets. But still, that time of my life, the first 18 years of my life in India, it did expose me to a lot of poverty, a lot of primitive forms of agriculture. And at Microsoft, that's what triggered me to start this project in 2014. In fact, the goal of this project is much more. The goal of this project, which was Project FarmBeats, is to help address the world's food problem. As many of you know, the world needs more food to feed the growing population of the world. Compared to today's levels, it's over 50% more food needs to be grown to feed the growing population of the world. And it is not just about growing food, more food, it's about growing good food, nutritious food. And we need to grow this nutritious food without harming the planet. The soils are not getting any richer, the water levels are receding. The world needs to grow more food to sustainably feed the world. One of the most promising ways to address this problem is that of data driven agriculture. One of the things you could do with data driven agriculture is you could map every farm in the world with data and overlay this with insights. For example, you could build a map, say what is the soil moisture level 6 inches below the farm throughout the farm, what's the soil nutrient level. If you could build maps like this, it could enable technologies such as precision agriculture. If you have a map of the farm, you could then apply water only where it is needed. You could apply nutrients only where it is needed, chemicals only where it is needed. And precision agriculture has been shown to improve yields. You can take care of the plants better. It has been shown to reduce costs. You would use less water, less pesticide, less nutrients. It's also better for the environment for the same reasons. You're not wasting water. You're not putting in more chemicals that are needed. In fact, it is not just about the production side of agriculture. Data and data driven agriculture food systems can help improve efficiencies throughout the agriculture supply chain, all the way from inputs to seed companies, to farmers, to distributors, logistics companies, to food processors. Every entity in the food supply chain would benefit by getting the data and then using AI to provide insights on top of that data. In fact, it is not just about getting data from each component, not just each component would benefit from data, but there would be much more efficiencies if every entity in the supply chain could share the data with other components in the supply chain. For example, over here, what you're seeing is a few examples. You could enable scenarios such as traceability. If, for example, you could share the information about where the particular food was grown and carry that information all the way through the supply chain to the retailer, to the customer, you could then see how a particular food was grown. In case of any outbreak, you can go and recall the particular food and for coming from that particular farm. There are many other techniques, the many other scenarios, business models that data sharing can enable. For example, you could enable precision agriculture techniques. If you could share this information of what's happening in the farm with the farm equipment, with the input companies, to the digital advisory providers, you could then light up new precision agriculture scenarios. Further, there is a lot of conversation going on these days around sustainability. As you know, agriculture causes a lot of emissions, but agriculture could also be a solution to climate change if you use the right agricultural practices in the farm. If the farmer can share this information about how the particular crop was grown to the entire supply chain, then the farmer could be reimbursed, could get the benefits of using the right agriculture practices. Of course, for that too, you need to be able to collect the data and share the data throughout the agriculture supply chain. These are just a few examples. In fact, there are many, many more. The thing is, precision agriculture as a technology was proposed back in the 80s. It's been 30 plus years since the time it was first proposed, and the technology still hasn't taken off. And the biggest reason this technology hasn't taken off is because of the cost of existing data driven agriculture solutions. These solutions are quite expensive. Just to give an example, I was visiting an expo back when I started this project. This was around in 2017. And there were several companies presenting their really cool data driven agriculture solutions. But the cheapest package for this was just the sensor package that was available for precision agriculture were 5 sensors for $8,000 and a recurring cost. For most farmers, for most growers, what is the ROI? What is the return of investment of putting 5 sensors in the farm and putting in thousands of dollars to maintain them and then having a recurring cost on top of it? So that was the goal when we started the FarmBeats project was how can you significantly bring down the cost of these solutions to make it affordable, to make data-driven agriculture affordable for farmers worldwide? In fact, one of the things we realized, which was the motivation of this project, was when I started the FarmBeats project, I went and I interviewed several farmers in the US, but also in other countries, in sub Saharan Africa, in India. What I realized is that every farmer knew a lot about the farm. They have been farming there for decades, and this is true for many of the indigenous peoples in Canada as well. You've been farming in your farms for quite some time. You know your land better than any AI. Yet, a lot of decisions that you take on the farm are still based on intuition and guesswork. For example, what do you plant? When do you plant it? When do you water? When do you fertilize? When do you harvest? A lot of these decisions are based on intuition and guesswork. Our vision with the FarmBeats project was not to replace a farmer, but can we augment your knowledge of the farm, of your farmland, with data and data driven insights so that you can then be empowered with this additional intelligence to take the right decisions at the right place at the right time in the farm. So, to do that, I'll talk about a few ways in which we are bringing technology to agriculture, making it really easy to capture large amounts of data from the farm, to bring this data to the cloud, and then use artificial intelligence techniques to bring intelligence, to bring insights to agriculture. I'll talk about a few of these innovations that we are working on. One of the biggest barriers to data driven agriculture is connectivity in the farm. The farmer's house might have some sort of connectivity to the cloud, but the actual farm could be few miles away. Sometimes, even though internet connectivity might exist when you plant the seeds, by the time the crops grow, the connectivity is gone. So the question then is how will you bring large amounts of data from the farm, which is a few miles away, to the farmer's house or office so that you can then start building insights on top of this data? To address this problem, we use a technology that I've personally been working on since 2005. One of the technologies we use is what we call as TV white spaces. This is using unused TV channels to send and receive data. So what TV white spaces enables is imagine if you have a Wi-Fi router that you can access a few miles away. That would be cool, right? Right now, as soon as you exit your house, your Wi-Fi disappears. And the way we did that was we took a Wi-Fi signal and we put them in empty TV channels. This is TV you watch using over-the-air antennas. You know, when you browse through TV on certain channels, you get a transmission. On other channels, all you see is white noise. The technology we built was a way to take a Wi-Fi signal and put them in these noisy TV channels in a way that doesn't interfere with your TV reception in an adjacent channel. So you could be watching channel 7 at home. On channel 8, we could be sending Wi-Fi signals. And the reason this is so cool is that compared to Wi-Fi at the same power level, in UHF TV channels, your signals would go 4 times farther. In VHF, they would go 12 times farther. And this is in free space. Once you put in trees, crops, canopies, your signals would keep going through. And this is something which we did back in 2010. The FCC chairman was here. This is the Federal Communications Commission here in the US. This was made legal in the US back in 2010. The interesting thing about agriculture is that the TV towers are where people are. You have TV towers in Seattle, you have TV towers in Toronto, in Vancouver. The farms are away from the cities. If you turn on a TV in the middle of a farm, most of these channels will be white noise. I was giving this talk at the National Controllers Association, and I gave an example that imagine if 20 TV channels were available in a farm, and there was this woman farmer from Kansas, and she raised her hand and she said, I only get 2 TV channels in my farm. So if you think of it, if even if 20 TV channels are available, and usually there's much more in the middle of a farm, you're talking of 20 times 6, that's 120 megahertz of empty spectrum, which is about half a gigabit per second or more of available capacity in the middle of a farm. At that kind of capacity, you can send large amounts of data from the middle of a farm. You're not just talking of connecting sensors. You could be connecting drones, cameras, tractors, streaming a lot of information that you just couldn't get in the middle of a farm. So the Canadian regulators have also been very proactive and leading the world in this. They have also created regulations around TV white spaces. So I have been working with Matthew Kopech and his team at Creative Metric over the past 18 months with Microsoft and the FCC on a novel solution to bring rural connectivity to Saskatchewan, closing the digital divide to underserved communities in agriculture. At Microsoft, so our vision here, as you can see, is that just like Wi-Fi connects your house, our goal is to use this technology as one example to connect your entire farm. You could put an antenna on a grain silo or the farmer's office and get miles around it connected to the internet. In fact, at Microsoft, we are taking one step further. TV white spaces is one technology. We are also looking at whether we can bring private 5G networks. That is, can you be running 5G scenarios over here? We are also looking at space connectivity, using satellites, these low Earth orbit satellites, as a low-cost connectivity method. The ultimate goal is how do you bring down the cost of connectivity in the farm? And we believe we have a way we can get there. The second challenge is that of sparse sensor deployments. I had shown you this map earlier. This map, suppose the challenge was, what is the soil moisture level 6 inches below the soil throughout the farm? If you had to accurately build a soil moisture map, you would have to put a sensor every 10 meters in the farm. But because soil moisture varies from row to row. But putting a sensor every 10 meters is expensive to deploy, to manage. It will come in the way of the farmer as the farmer does the day-to-day job. So the key question we asked was, can you build an accurate map, say for soil moisture, soil temperature, soil carbon? Can you build an accurate map of the farm using very few sensors? To address this problem, we decided to use AI. That is, instead of just using sensors, we are using a multimodal technique. That is, we complement sensors and combine them with aerial imagery, say from drones, or in places where you don't have drones, we use balloons, where a farmer could put their camera on a mount on a balloon which is tethered to the ground, and it stays up from 4 to 7 days. So that is another way in which you can get aerial imagery. In fact, for other regions where you don't have drones or balloons, we use satellite imagery as well. We use this aerial imagery from the farm and then use computer vision techniques to build these accurate 3D maps of farms, these orthomosaics of farms, where then we use artificial intelligence to determine what are the best places in the farm you need to sense. You need to put either a sensor or you need to get a soil sample. So once you get these samples, then what we do is we use artificial intelligence and machine learning to combine these sensor streams to build these kind of heat maps, the one you're seeing on the right. In particular, the way the system works is wherever you put a sensor, we look at correspondingly what does the image look like. That is, for that point in the farm, what is the RGB, multispectral or hyperspectral values for the farm? We do that for every place where you have a sensor. And then we use this mapping in the optical domain to create a machine learning model, which we then use to predict these values in other parts of the farm where you don't have a sensor. And we've done this for soil moisture, soil temperature, soil pH. And we wrote a research paper on this where we showed that using this technique of combining different data streams of sensors with aerial imagery can give you 3 times more accurate maps than existing schemes that do not use aerial imagery. And this is a research paper we wrote, which you can find on my website. One of the challenges, though, is that you can't always get aerial imagery from satellites. Satellites are great, they give you global coverage, but satellite imagery cannot see through clouds. A lot of times, if you ask for historical imagery for a certain location, you'd probably get a couple of clean cloud free images for any farm over an entire month, or maybe even fewer. So then the question was, well, if we have to build these maps and generate insights, and we are not getting an up to date map of the farm because of clouds, how do we generate these maps? To answer this question, we built a technology called SpaceEye. SpaceEye, the goal of SpaceEye is to see through clouds in satellite imagery. And the way we do that is we combine data from existing satellites, which collect optical imagery, with another satellite that goes around the Earth, which has SAR in it, synthetic aperture radar. Radar signals, these are radio frequencies, go through the clouds and they reflect differently from different surfaces, say from a soil that is moist to a crop that is dry, crop that is under stress. We use all of this information to then reconstruct what's happening below the clouds in satellite imagery. Behind the scenes, we use technologies such as GANs, generational adversarial networks, which are used in deepfakes. You must have seen these deepfake videos where you take a video and then you can overlay someone else's image with somebody else. We use a similar thing here for clouds, but instead of fake, we try to create something real based on the synthetic aperture radar imagery. So as you can see in this video, on the left is the imagery we get these days. That is, as you can see, it's mostly cloudy. On the right, we are able to see through the clouds and create these satellite images. And you can see when a field has been tilled, has been planted, when the emergence happened, when it has been irrigated, and all of this, even though existing imagery was just cloudy. And in a paper, this is a paper that we've just written as well, where we've shown that we are getting over 95% accuracy in these images for 3 of the 4 seasons, for spring, summer, and fall. Of course, in winter, we are still working through snow and clouds. We get close to 85 to 90% accuracy, but for most of the other seasons, the results are very promising. The third challenge, I talked about how we can reduce cost of connectivity, how we need much fewer sensors than what you would otherwise need using the multimodal fusion technique I just talked about. The third challenge is, you know how I talked about you could get a lot of data from the middle of the farm to the farmer's house using technologies such as TV white spaces or private 5G networks. But the connectivity from the farm to the cloud is often weak. Many farmers, they pay for broadband, but all they get is 1 to 3 megabits per second connection. And it's not just that, this connectivity is also intermittent. There is this farm in upstate New York where every time there is a snowstorm, there's a high likelihood that his internet connection would go off. So, and just to talk about the weak connectivity, 1 to 3 megabits per second is not enough for many of the scenarios we were talking about. That is, just to put this in perspective, every time you fly a drone, in a 15-minute flight, you could be getting a few gigabytes of data. You can't send a few gigabytes of data over a 1 to 3 megabit per second connection. It would take days to send all of this information to the cloud. So then the question is, if you cannot send all of this information to the cloud, then how will you get benefits of all of this data to the grower? To answer this question, our key insight was that many farmers we talked to have a PC. If they don't have a PC, we would ship them a PC form factor device that would stay in the farmer's house or office, and it could do a lot of compute sitting in the farmer's house or office. It could get the data, it could do all the computer vision, the artificial intelligence on that computer in the farmer's house, and then relay some of the summaries to the cloud, where you could add additional insights on top of this for the growers. So just double clicking on what's on the edge, what's running on the edge. As you can see in this figure, everything running in the big gray box is running on the edge device. It's a PC It gets data from sensors, it gets data from drones. It then generates the panorama, the orthomosaics, the 3D views I talked about using computer vision techniques. It combines them with sensor data to build these build the heat maps. And then this flows into the last column where you see all these agricultural services, which Microsoft, we are not the agricultural experts, but we would work with our partners to build these components that you're seeing in the rightmost column. In addition to that, we ingest data from cameras, we do deep learning on the edge, and not all of that data is immediately sent to the cloud. We have storage, and we also have a web server that sits, that is able to, so that you can access all of this information even when there is no internet connectivity. We've also come up with an intelligent way to synchronize all of this data with the cloud. What we do there is once, for example, you take large amounts of imagery, rather than sending all of the imagery to the cloud, we will extract parts of the images that are more important and send them first to the cloud, while then sending all the other images to the cloud. So then I just wanted to mention this was all in research when we were building the FarmBeats technology. We then started deploying it in a few farms. We deployed it in farms all the way from a small farm, which is like half an acre, all the way to big farms, up to 9,000 acre farm. This is one of the farms in eastern Washington, which is spread across 45 miles. I'll talk about a few of the use cases. What you're seeing here is microclimate prediction. As you know, for farmers, knowing the weather, knowing the hyperlocal weather is very important. Many farmers, they look at the predicted weather forecast from the weather station, but that's the forecast at the weather station. It could be very different from the weather in the farm and in different parts of the farm. One of the things we've done as part of this technology is when a farmer puts a sensor in the ground or a weather station, we'll not only tell you what the values are right now, but we'll make these predictions up to 5 days in advance of what these values are. And the way we did that was we took weather station data from 50 weather stations across Washington state over the last 7 years at 15-minute intervals. We used that to train a machine learning model. And then when you put a sensor, we then use that trained model to start making very hyperlocal predictions for that farm. What you're seeing here in this figure is if you look at the red bars in this figure, for soil moisture and soil temperature, even up to 5 days in advance, our error is less than 8%. At the bottom left of the slide, you're seeing a testimonial by one of the farmers. This is the farmer in eastern Washington who farms 9,000 acres spread across 45 miles. He was going to spray herbicide in his farm. He looked at the predicted weather forecast. The predicted weather forecast was 42 degrees. We said it was going to be 31 degrees. It was actually 30 below freezing. It was good that the farmer did not go and spray chemicals in the farm because otherwise he would have lost his entire crop. This is another use case where this is a 4-kilometer stretch. The farmer, this is in upstate New York, the farmer wanted to know how his cows are doing in pasture. So we flew the drone, we transmitted the data over the white spaces to an edge device where we started doing AI. And within 30 minutes, we could start flagging things like from left to right, the grass is growing back well. There is a water puddle that needs to be fixed before the next planting season. The cows are pooping well, which was also important information for the farmer. This is deep learning on cow poop, that is AI on cow poop. This is where the cows are. This is a stray cow that needs to be herded in. All of this within 30 minutes of flying the drone. This is another farmer we used to work with close to Microsoft campus. This is a small farmer. He sells vegetables to restaurants in the area and in the farmer's market. We show the farmer these beautiful pictures. This is a farm where we did a lot of demos. We hosted several executives. Bill Gates spent time in the farm and he wrote about it on Gates Notes as well. So to this farmer, we show these beautiful pictures and we overlay this with data. For example, this is a soil moisture map. We were able to flag that the bottom left part of the farm is still moist, even though we did not have a sensor over there. What you're seeing here is a pH map. After the farmer had applied lime, we were able to flag that these dark parts of the farm are still acidic. The farmer needs to reapply lime before planting the seeds. This is another use case where this is a barn in upstate New York. We had 3 cameras and we are monitoring how the cows are doing, transmitting the data over the white spaces to an edge device where we are seeing how the cows are moving, whether a cow has fallen sick or whether, and this is like, imagine like a baby monitor for cows. And the reason you could implement it is because you can transfer all of this data for cheap. You can use AI at the edge and use edge compute. So all of these technologies coming together to light up scenarios where we can bring data and AI and intelligence and insights to to growers, to the agricultural community. So then, just telling you about my story, I moved over to the product side and we shipped a product called Azure FarmBeats. We announced public preview in November 2019. So what we're doing with Azure FarmBeats is, right now, there are several ag tech companies, agriculture technology companies. What they do is they take data from a variety of sources. They take data from sensors, from tractors, or not all. We don't know of anyone who does all, but they write their own pipelines for some of these data sources. They would then try to write AI and build solutions for, like for example, for precision agriculture or for sustainability. What we're doing with Azure FarmBeats is taking some of these common components, the technology stack, and infusing it with the innovations I just talked about. Either we bring the innovations directly to the stack or work with partners where we license some of these technologies to our partners to bring the innovations that we talk about to the agriculture domain, to Azure FarmBeats and our partners. So with Azure FarmBeats, what we are doing is it's a cloud platform where, and it's not meant to be farmer facing. So Azure FarmBeats is meant for ag tech companies who would then build their solutions and take it to the growers. With Azure FarmBeats, the APIs that we're providing is a grower can then define a polygon, which is any area, which could be a farm, a field. And for that polygon, we would bring in data about the farm from different variety of sources, from satellites, from weather stations, from sensors and other sources, all of this to the FarmBeats platform. And once you get all of this to the FarmBeats platform, then we provide this analysis component, this AI component, which would then enable our partners to build their ag tech solutions on top and take these solutions to their customers, who are the growers. As you can see, Azure FarmBeats is a very partner-led offering where we ingest data from a variety of partner sources. This could be the satellite companies, the sensor companies, drone companies, tractor companies. Most recently, we announced an integration with DTN, which is a ag weather provider, into Azure FarmBeats. And once we get all of this data, we've also announced we build solutions for customers with partners. Like, for example, we announced a partnership with Land O'Lakes, with USDA. With Land O'Lakes, our partnership revolves around three different pillars. One of the announcements Land O'Lakes made was that it would build all of their ag tech solutions on top of Azure FarmBeats. We are working hand in hand with Land O'Lakes and with a partner called Tavant to take all of the existing ag tech solutions from Land O'Lakes and build it on top of Azure FarmBeats, bringing all the innovation that we are talking about to the platform, along with the deep expertise that sits with Land O'Lakes. We're also working with Land O'Lakes on connectivity, providing rural broadband connectivity. We're also working with them on sustainability with Truterra, Land O'Lakes sustainability platform. In addition to that, we also recently announced a partnership with USDA Agricultural Research Service, where researchers at USDA are using Azure FarmBeats in their research farms and building solutions on top. At Microsoft, in addition to the research and the product side of things, we are also doing more and invest and trying to work on ways to take these innovations all the way to the growers and to the rural communities. One of the things we are doing is we are investing in rural broadband through our Airband initiative. And as part of the Airband initiative, we are investing in licensing the technologies, providing grants, creating ISP and standard strategic partnerships, and working with several stakeholders to bridge the rural broadband gap. As part of this, I talked about TV white spaces as one of the technologies that we have. And through that, there are some partners. For example, Six Harmonics in Canada is doing some very innovative work using the TV white spaces spectrum for providing connectivity in rural areas of Canada. One of the other things we are doing is around sustainability. Last year in January, Microsoft made a big sustainability announcement. We said that by 2030, we are going to be carbon negative. What that means is that we are going to be putting back more carbon in soil than the amount that we generate. And it's not just that. We said that we're going to by 2050, we will remove all the emissions that we've ever generated since the time Microsoft was founded. And towards that, our CFO, she put in $1 billion to make it to help us invest in technologies that can help us get there. So how will we get to carbon negative by 2030? Part of it is by reducing our own emissions. We are investing in technologies for carbon removal, and the part of it would be by reducing our own emissions, but the other part is we would need new ways to put carbon back in soil. And as many of you know, agriculture can be a potential solution. So, agriculture has a very interesting role to play in climate change. As you know, agriculture creates a lot of emissions, both in terms of carbon emissions, methane emissions, nitrous oxide emissions. These are all greenhouse gases that impact climate change. In addition, agriculture is also the most impacted by climate change. Farmers depend on weather. They've been doing the same thing for decades, if not centuries. These farmers, when things change, when the weather takes an unpredictable turn, the farmers are impacted the most in their agricultural practices. The third thing, though, is that agriculture can actually be a solution to climate change. One of the solutions. If the farmers use the right practices, the plants can then help pull some of this carbon from the atmosphere and put it in soil. With just because of photosynthesis, as you know, these plants could take some of the carbon dioxide. And if the farmers use the right agricultural practices, what we mean by that is these regenerative agricultural practices, things like cover cropping, or doing the right nutrient management, or practicing no-till or reduced-till. These are all ways in which you could put more of this carbon back in soil, increase the soil organic carbon content. Of course, one of the problems there is, how do you accurately estimate the amount of carbon that is sequestered in soil? This is a hard problem, where again, we are bringing in technology, bringing in artificial intelligence, new ways of Internet of Things to help quantify the amount of carbon that is sequestered in soil at a low price point. In fact, we are doing some work with one of our partners in Canada, Terramera, who's coming up with new technologies to estimate the amount of carbon that is sequestered in soil, to enable growers to know how much carbon is being sequestered so that they can practice the right agricultural practices. One of the other work we are doing is working with the future farmers of America. We are trying to help the next generation of farmers be trained in data, in technology, in artificial intelligence. One of the things we did was we built a small kit, which we then gave out to high schools, and then helped form a curriculum as well, so that high school students, when they are learning about the regular subjects, they also learn about data, they learn about AI, and they learn about how they can use all of these in the context of agriculture. Our vision here is that with all of these technologies, we can help make agriculture cool again. In addition to that, we work very closely with universities as well. As many of you know, during COVID, agriculture and growers got impacted a lot. Many growers, they couldn't sell their crop because they had no visibility. They did not know how to sell all of the produce that they were growing. In addition to that, many meat packing plants closed. There was a lot of disturbance to the entire agriculture and food supply chain. One of the work we did with Purdue University was to add more visibility to the agriculture supply chain. We brought in various open data sources. This is work done with Microsoft Open Data Campaign, Purdue University, and Microsoft Research, where we brought together a lot of this data and then built this dashboard using Power BI, where you could go, and we took COVID data, and then what you could do is you could look at commodities, and for different counties, you could see what is the risk of that commodity in that particular county. This was work done by Professor Jason Lusk at Purdue, and we recently published a paper on this work as well. So until now, you saw a lot of work that we're doing in the agriculture space. We talked about some of the new R&D we are doing. I talked about some of the products that we are building in this space, and also some of the future-looking, some of the ways in which we're working with our CSR initiatives to take all of this and take it to the rural communities, take it to the growers. And of course, the way we do all of this is through our partners. Microsoft is a very partner-led company, and this is just a few of these companies. We're working with many other companies that are not necessarily listed on this slide. For example, I mentioned Terramera, Cropmetrics, and others who are also companies that we are working with. The one thing I wanted to leave you all with is, where are we now? What are the new things we are looking at? I talked a little bit about sustainability, about supply chain, which are top of our mind, which are things that we are thinking about. One of the things that we're thinking about is smallholder farmers. There are a large number of smallholder farmers worldwide, not just in the emerging markets, but also in the developed world, like in the US and in Canada, especially in the indigenous communities. So, one of the questions that we have been asking is, okay, how do we enable, what are the hard problems we need to look at to, to drive the adoption of digital agriculture techniques for smallholder farmers? So this is work I did with the Gates Foundation, with Stuart Collis at the Gates Foundation. We wrote a paper which will be published very soon on looking at challenges and opportunities to enable digital agriculture for small scale producers. So we looked at this. We actually did a survey of existing technologies, and we actually put all of this in a hype curve. You know what this is? This was originally proposed by Gartner, and here what you're looking at is on the x-axis, it shows the evolution of some of these technologies, and these are different technologies that have been proposed. They start with the innovation trigger. They go through a lot of inflated expectations, then this trough of disillusionment before you have the slope of enlightenment, and it actually takes off. As you can see, most of the technologies for smallholder farmers for precision agriculture are in the trough of disillusionment and before that. And one of the biggest reasons this is the case, we looked at, okay, what are the reasons this is the case? And we found some of the core, I'll talk about four key reasons. One is around affordability. Many of the technologies that people are proposing for large scale agriculture isn't yet affordable for small scale farmers. Another challenge is that of connectivity. Many of these farms do not have good, affordable connectivity. In fact, there was a recent study by the USDA which said that over 75%, around 75% of farmland does not have broadband connectivity. In fact, in the rest of the world, if you look at sub-Saharan Africa, India, and many parts of the world, what is found is that only 60% of the world's population is connected to the internet. 40% are not, of which 30%, the 30% of the world's population is not connected, not because they do not get a signal to connect, but because the connectivity is not affordable. So one of the challenges we have is, how do you make internet access more affordable and not just internet, broadband internet, if possible. The third challenge is that of relevant data. A lot of the data for small scale farmers is hard to capture. It still sits in analog form, or it never gets to the cloud. It sits in isolated silos. It is not shared, so that you can't run your AI. You cannot run your artificial intelligence models on top of that data. That is another one of the challenges that needs to be addressed. Another challenge for smallholder farmers around relevant data is that if you look at satellite data, each pixel for a particular small farm, you're only getting very few pixels. And many farmers in the same farm might plant multiple crops. In fact, in India, they plant 9 crops in the same hectare. So what you're getting is very few pixels out of which you need to extract information. So that is another one of the hard problems. The fourth challenge is that of usability. Many of the farmers are not the most tech savvy people. Well, farmers, the more farmers I've talked to, I've realized they are super talented. They are agriculturists, they are electrical engineers, they're mechanical engineers, they do a lot of things. They're very talented. Yet technology is something which is not their strength. So what that means is, as we are developing technology solutions, and if we want it adopted by the smallholder farmers, we need to make that technology more usable. One of the technologies that we are investing on is on conversational AI. That is, instead of going through your phone and swiping and so on, can you just talk to your device. It will also help with farmers whose hands are soiled. They can just talk and start getting information. So these are some of the things that some of the reasons why most of these technologies haven't taken off yet for smallholder farmers. One of the other cool technologies that we're working on, this is early in research that we're working on, is on affordable sensing. That is, most of the sensors that you can buy still cost a few $100s, if not up to $1,000, for example, to measure the electrical conductivity. One of the questions we asked was, can we make these sensors more commodity? That is, at a few $100s or $1,000, most smallholder farmers can't afford that much money to deploy one of these sensors in the farm. So then the question was, one of the ideas we had was, well, one way you could bring down the cost of these sensors is by leveraging the smartphone itself. That is, the question we asked was, can we use the Wi-Fi chipset in the phone to measure soil moisture and soil EC? That is, many farmers, they won't spend a few $100s or $1,000 buying a sensor, but many of them have a smartphone, even if it is an inexpensive smartphone. If they have a phone, it has a Wi-Fi chipset in it. So if it has a Wi-Fi chipset in it, the key idea was that if you could measure the time of flight of a Wi-Fi signal, you can use it to measure soil moisture and soil EC. That is, based on physics, the time of flight of a radio frequency signal like the Wi-Fi signal depends on the permittivity of the material. So if your soil is moist, it will take longer to traverse the same distance. The challenge is this time is of the order of nanoseconds. How will you measure this time in nanoseconds? Which is where one of the key ideas that we had, this was done by one of my interns, was, well, if your smartphone has multiple antennas, most of the chipsets, if you have multiple antennas, you could then measure the time difference of arrival instead of the absolute time and use that to measure soil moisture and soil electrical conductivity. We actually compared the results we got with some of the equipment, some of the sensors that are commercially available, and we got very good results. This was a research paper that we wrote on this. It got an award at a top tier computer science conference. We showed it to Bill Gates when he visited the farm, and he wrote about this in Gates Notes. And the title of the Gates Notes blog was, "Can the Wi-Fi in your phone help feed the world?" We are very bullish on this technology. That is, we envision that in the future, a farmer could just come with their phone close to soil or take samples of soil, bring their phone around it, and know what's going on in the farm. Or put this phone in their pocket and drive around and get an estimate of what might be happening. This is still a vision of what can be enabled in the future, but our initial results look promising. I wanted to conclude just by talking about some of the hard problems for entrepreneurs who are here, who are looking at what are the hard problems that they need to solve if they need to get to the smallholder farmers, either academics, VCs, donor agencies, governments. This is all for you, just some ideas. On the x-axis, you're seeing a lot of these digital technologies. On each column here, represents the hard problems that I talked about around connectivity, around affordability. And these are just some of the problems that exist. The ones in green are the ones that are more mature, even for large farms and for smallholder farmers. We are seeing more use of those technologies. The ones in yellow are the ones that need more research, and the ones in red are the ones that are still very early. Those are the ones which need a lot more innovation if we need to see adoption of these technologies for smallholder farmers. If you were to take the main takeaways from this slide, well, some of the work on satellite-based remote sensing or sensors are more mature. They are more likely to see early adoption for smallholder farmers. The other thing to look at is, if you look at the third column on AI is going to improve every existing digital technology and make them better. But one of the key opportunities here, for example, is the fourth row from the top, the one with drones and robotics. A lot of hard problems exist across all dimensions: hardware, AI, security, as well as human interface, to get these technologies off the ground and usable by smallholder farmers. So with that, I wanted to conclude and thank you again for the opportunity to speak to you all. My contact details are here. Please do feel free to reach out. I'm very passionate about this space. At Microsoft, we are doing a lot to help with agriculture, both for large scale farmers, for smallholder farmers, and we are doing work with indigenous communities and would love to do and would love to do more, both directly with the indigenous communities plus with partners who are working with the indigenous communities. So please do feel free to reach out. Thank you again, and hope you have a great conference. Bye.